Good evening, folks, and welcome to the Advent of Code C++ live stream. My name is Craig, and tonight, as every night, we're going to be working through Advent of Code puzzle solutions in C++. Thank you, everyone, for watching, whether you're watching the live stream on Twitch or you're watching the replay later on YouTube. If you're watching on Twitch, you can go to my channel profile, and there you will find links to my YouTube channel with all the stream replays for all these Advent of Code live streams, plus a link to the GitHub repo where all the code that we write is uploaded. If, on the other hand, you're watching on YouTube, you can just check the channel description right down there. Excuse me, the video description right down there. And you'll find links to the Twitch channel for live streams, and once again to that GitHub repo where we post all of the code. So we have just a couple of minutes until tonight's puzzle unlocks. Excuse me. I really enjoyed last night's puzzle, and I actually went back and refined it just a little bit by kind of generalizing the stuff that we were doing with the folds. And I went into my 2D geometry library, Grid 2 here, and I added a new concept, a new struct for a line. And right now this line can only be horizontal or vertical. It doesn't, it doesn't support lines with a slope, a non-zero slope. But it's still enough to represent those fold lines in last night's puzzle, and we can reflect across this line. We can also subtract. We also have a subtraction operator between a point and a line, which will give us the normal vector from that line to the point. So we've kind of integrated the geometry that we needed to do last night into that library in case we need to do something similar again. I also went ahead and just added this static method to the point struct, this parse coord pair, which will just parse a pair of coordinates, just like we needed to do for all of the input points last night, in case we need to do something like that similar again. And then I went and modified my solution for last night to use this new stuff. If I had a little more time, I'd probably put this render points thing in, make it templatized so it can use any kind of container, and go ahead and put that in the library as well. But we've only got about 1 minute until tonight's puzzle unlocks, so we're not going to be able to do that before tonight's puzzle. One thing I would like to do before tonight's puzzle, though, is just get a skeleton program set up for it for day 14. And we'll go ahead and include the check and IO libraries that I use pretty much every day. And we'll add those to the deps in the build file that tells the Bazel build system that we're using how to build this stuff. And now we can go ahead and have Bazel build and run it for us. Okay, good to go. And just in the nick of time, because the puzzle just unlocked. Okay, day 14. Extended polymerization. Incredible pressures at the depth are starting points on your submarine. We have polymerization equipment that could produce suitable materials to reinforce the sub, and nearby volcanic caves should have the necessary input elements in sufficient quantities. Ooh, it's a recipe solver. I remember we had something like one of these for previous years. It offers a polymer template and a list of pair insertion rules, your puzzle input. You just need to work out what polymer would result after repeating the pair insertion process a few times. So we have NNCB. This is the starting point of the process. Following section defines pair insertion rules. A rule like AB goes to C means that when elements A and B are immediately adjacent, element C should be inserted between them. These insertions all happen simultaneously. So starting from NNCB, excuse me. Sorry, excuse me there. The following section defines, so starting from NNCB, first pair matches NN to C, so C is inserted in there. Second pair matches NC to B, so B is inserted there. Third pair matches CB to H, so H is inserted there. Note that these pairs overlap. The second element of one pair is the first element of the next pair. Also, because all pairs are considered simultaneously, inserted elements are not considered to be part of a pair until the next step. Okay. This polymer grows quickly. After step 5, it has length 97. After step 10, 3073. After step 10, B occurs, so we've got counts of the various elements. Taking the quantity of the most common element and subtracting the quantity of the least common element produces this. Okay, so let's go ahead and get our input here. day14.txt. Let's take a look at what that looks like. day14.txt. Okay, so we've got a lot of rules, and we've got our initial polymer there. So first thing that we're going to do is just read all this stuff in. So we'll say we'll have a vector of strings that are the input lines to the program that we will read using our read lines from file function, using argv1, the first argument to the program, besides the program name itself. And then we are going to split this up. Well, actually, you know what? The first line is the initial polymer, and then there's a blank line, and then everything after that should be a rule. So we'll go ahead and say that polymer equals lines.front. And then when we're parsing these rules, we will start from 2 past the beginning. So to store these rules, we're going to use a hash-based map. So I'm going to use absol flat hash map. And we're going to map string views for those 2 character pairs to just char for the 1 character that gets inserted in those pairs. And we actually need to put in the include here because autocomplete is not finding it. Flat hash map. Okay. If you did not have a if you're not using absol flat hash map, you could do exactly the same thing with unordered map in the standard library. Let's go ahead and say for auto rule it for the rule iterator, and we're going to start at lines.begin +2. We're going to skip the first 2 lines in the input, and then does not equal lines.end. We'll increment that iterator, and then we will do rules.inplace, and a rules.tryInplace I think is actually going to be a little easier to do here. And the first part of it is going to be lines. Actually, we'll go ahead and just declare a string view rule stir by dereferencing that rulet, and it's also going to convert it from a const reference to a string view. Although I realize, these are all 2 characters, this is maybe even overkill, but, we'll just stick with string view for now. So we'll say rule stir dot substir from 0 to 2, those first 2 characters, and then the last one in the line should be rule stir dot back for that last character. And now we have our set of rules. So now we need to write a function, and we'll put it in an anonymous namespace here, but we need to write a function that applies all of the polymerization rules to that polymer and gives us our new polymer. So we could wind up doing a whole lot of splicing in this string, and I'm almost tempted to have like a linked list of characters, which would blow up memory a whole lot, but would avoid a lot of copying. But for now, I'm just going to do the simple thing and just keep things as a string. So we'll say polymer, and then we'll do a const reference to these rules. So we have to start at least, well, so we're considering which two characters to splice something in between. So, you want to start at one maybe? I don't know. Yeah, this is going to be easier than modifying in place for sure. And we'll only copy characters when we need to. I think that that is going to be the way to do this. So for although I am now realizing that maybe instead of doing a string view, this might actually be easier at, we'll be fine. So we'll say if a new polymer will start with the first character of the original polymer in all cases. So now we'll say if we'll try and find in the rules something that the subs we're going to try and find polymer.substring from pos -1 through to and 2 characters beyond that. So so that will cover pos -1 and then pos itself. So if no rule applies, then we will just push the molecule or element or whatever as is onto the chain. Otherwise, we're going to put the spliced in one in there, and then before we do that. So actually, no matter what, we're going to be doing this. So let's change this logic around a little bit. So if we do find a rule, we'll put that in, and then no matter what, we'll put the second element in, and then return new polymer. Okay. So after 10 steps of pair insertion of the polymer template, find the most and least common elements of the result. Okay. So I is 0, I is less than 10, plus plus I. We are going to replace Polymer with apply rules on that Polymer. Although, I'm realizing now we don't actually need to move or do anything with that, so we'll just keep Polymer as is in the input before we reassign it. And we'll give those rules there. And now we need to find the most and least common elements in the result. So I don't know if we want to do that in a map exactly. Yeah, it's fine. For each element in the Polymer, well, we should declare this first. We will say, we will increment the count for that element. So that subscript operator there is going to create an element in counts if one does not exist for a given element the first time it encounters it. And it's going to default initialize the mapped value to 0. So that should give us the yeah, the map of elements to counts, and then I think we can use something here. Yeah, so we'll say element counts equals element counts over that modified Polymer after 10 iterations, and then we can do I think we can use standard min-max element to find what we want here. Yeah, okay. So this min-max element, what we can do with this is we can give it the iterators over element counts to search, and it's going to return us the iterators to the minimum and the maximum value. But because these are pairs, we have to give it our own custom comparison function to basically teach it how to compare those. And I'm using auto very liberally here instead of like spelling out what the derived type names are, because it's going to give us pairs, so we just want to do return L.second less than R.second, because we want to compare the second element of the pairs, which is the actual count. And then what we actually want to print out is the largest minus, is the max minus the smallest. So we'll do standard cout, and then we will do star to dereference max it. Oh, no, we want max it pointing to the second, the actual count in that pair, minus min it pointing to its second, the actual count there. And that should be the result that we want. So to actually build this, we're going to need to add dependencies on the flat hash map and strings here. So doing copy pasting with minimal modification here. And let's go ahead and try to run it on our input for day 14. Okay, it says the difference is 2,587. Let's see if that's correct. Bomb, bomb! All right, we got the first one. The resulting polymer isn't nearly strong enough to reinforce the submarine. You'll need to run more steps of the pair insertion process. A total of 40 steps should do it. Oh my. That is going to produce something super long. Wow. Okay. So we have to think of something here. I'm seeing these numbers are so huge here that we can't really actually produce the string. We would run out of memory. So we need to do something a little more clever about this. So first thing we'll do is go ahead and make a commit for our part 1 solution here. And then we'll copy it over and start tinkering for part 2. So there's a few things we can kind of try and do here. For one, we can we could try and see if there is like a mathematical pattern that we can see just from applying, you know, multiple steps here. So I'm going to go ahead and in part 2 here, just take this whole thing that prints out that result part and see if it shows us anything interesting. If a numerical pattern jumps out at me. So let's go ahead and run that modified version of our program here on our input. So 6, 10, 20, 38, 60. And so, so, and I'll do one more, you know, before any here. Not immediately obvious what's going on. I wonder if instead of generating the whole string, if for each iteration of this, we just kept track of the counts of pairs. Because that's all that should matter, I think, for generating new pairs in the next one, and that should be actually tractable. I think that that is the key here, is that we just keep track of the counts of pairs. We don't actually generate the whole polymer. So we'll go ahead and make a class here called compressed polymer that represents not a full polymer, but this compressed representation. And we'll say that lat hash map, And at this point, I actually am going to switch to using just arrays of 2 characters for the sake of being super efficient here. And then we'll use int64t, a 64-bit integer, to represent the counts. So we can have a constructor for compressed polymer, which will take that uncompressed string representation of a polymer and then build up these initial pair counts. So for position equals 1, position is less than the size of that uncompressed string plus position, and then we'll say pair counts at for those 2 adjacent characters, so pos -1 and uncompressed at pos. We will just increment that. Okay. So that's our compressed polymer representation. And then the way that we get a new compressed polymer representation, we'll just say, you know, compressed polymer, apply rules, and the rules, I want to make, I'm going to change that to use just an array of 2 characters representation as well, and we'll go back and change the parsing so that everything works. But yeah, that's going to be standard array of exactly 2 characters mapping to another character. So we'll say next here, and then for each pair in the input, we if that pair, yeah, so we can go ahead and we'll give this a default constructor as well that is just an empty compressed polymer. But what we will do is for because I'm obsessive about the style guide that I use, that needs to have a trailing underscore. So pair to count in pair counts. Auto rule it. So we're going to try and look up a rule in rules that matches the first element of pair to count there, which is just the pair of elements next to each other in the existing polymer. So if we don't find one, so if we get an iterator to the end of that container, then all that we do is just any pairs like that that appear in the input are just going to be copied over as is. So next dot insert, sorry, next dot pair counts dot insert pair to count. It actually, we better make sure that that is, no, we don't need to actually necessarily make sure that's newly inserted, now that I think about it, because other rules could produce more of that same count. So I'm just going to say next pair counts pair to count dot first, which is the first element. You know, sorry, I keep on changing my mind about certain of these things, but actually now that I'm thinking about it, I want to do pair and count, and then because that's just going to make it easier to refer to that. And so we'll say for that pair, plus equals count. So we'll just add to the count of the next one for that. And then we'll go ahead and continue because we don't need to do anything more for that. Otherwise, if we do have a rule, we're going to be adding the count to two different pairs. We're going to be for the pair in the middle, for the beginning in the middle and the middle and the end for that insertion in the polymer. So we'll say so that will be pair 0, the first element, and then rule it to second is the character that it maps to. So that we will increase by count. And similarly for the middle and the second character there. So that should be pair 1. And then we can return next. So the only other thing we need from compressed polymer is to be able to score it, basically, to find the minimum and the maximum elements in that pair counts array and find both of them. So I'm going to copy this just to give us the structure of it. It's not going to be exactly the same. Instead of element counts, it's going to be pair counts. Oh, no, we still do want the element counts, don't we? That's right. So, easily done. We're going to build up the element counts here by just going through the pair counts. So to get the element counts, all that we actually have to do is for all those pairs and counts in the pair counts map, we just increment element counts for both of the elements in the pair. So element counts pair 0 plus equals count, and the same thing for pair 1, the second element in the pair. And then this works exactly as is. And we return the difference between the maximum and the minimum counts. So you can get rid of that apply rules and element counts there. Don't need that anymore. We'll say we'll use compressed polymer this time. Construct it directly from the front line. And just for kicks, let's do it for an iteration of 10. Again, we'll say polymer equals polymer dot apply rules with those rules. Have it overwrite itself there. Is that not? Oh, yeah. Sorry. We need it. As I said before, we're going to need to change this to a fixed size array of 2 characters to work with the changes that we made before. So you rule stir 0 and rule stir 1. Okay. And then at the end of this, we print out polymer dot score. Now let's see if just it gives us that same result for the first day. Okay, that's not correct. So what did we screw up here? Let's go ahead and print out the score, you know. Compare it to what we were getting before and see how quickly it screws up. Okay. I think it's the scoring function somehow is messed up. Because before we do anything, it should be 3, and it's reporting 6. So obviously something is amiss there. So I'm going to get rid of all this business, but I'm just actually going to have it while it is counting, before we return this min-max stuff, I'm just going to, for going to go ahead and just print out what it thinks the element counts are for each of these. So we'll do element and see how that looks. Okay, so it believes that in the initial string, which for my input here is this. So that has 8 H's. I don't think it has 8 H's. 1. The single F, it's doubled the counts for everything, it seems like. No, it can't have doubled the counts because it thinks V is 3. And V is actually, although one of the V's is in front. Have it print out pair by pair while it's parsing. I'm actually relatively confident in the algorithm here, but I might be missing, you know, something weird with the parsing. So, you know, we shall see. HC, CK, KB. Yeah, that's all. KL. Oh, you know what? Actually, the scoring is going to be wrong because of pairs. Every individual element is going to appear in two pairs except for the first and the last. And, okay. Okay. So we should keep track of the first and the last here. And that is why everything looked to be even except like V there, because V was one of the first. So I think we might as well actually double this up and then just have everything in element counts. So we'll say we'll give one extra to the first and the last to account for the fact that those are the only not double counted occurrences, and of course, you know, we need to make sure to initialize those here. So say first compress dot front, last compress dot back, and make sure that we set those properly here. So next dot first equals first here, next dot last equals last here. The endpoints can never change because there's nothing on the other side of them to form a pair for insertion. And then make sure that this is divisible by 2, and then divide it by 2. Sorry, element counts. That's of course what we wanted there. Now let's see if that gives us a good initial one. Yep, let's see if it gives us a good end result for the part 1 version of the problem. Yep, that's what we wanted for part 1. Can go ahead and take out that debugging string there. Yeah, that works fine for part 1, and so for part 2, we just need to figure out what happens after 40 steps, which I think, thankfully, to this clever solution will not totally blow up memory. That is a big-ass number. Let's see if it's correct. All right, we got it. So let's see how we did on the leaderboards here. Okay, first one about 2,500. Second one 1,608. Not bad. So I think that on the second part of this puzzle, the algorithmic insight that we only need to keep track of the counts of the different pairs of elements next to each other was absolutely the right approach. We had that right from the beginning. What tripped us down was actually just calculating this score because, of course, any given pair the first and the second element of that pair each belong to two pairs, except if unless they are the very first or the very last element in the entire polymer chain. So that's why our count was a little bit off, and we needed to fix it up here. Um, but yeah, I'm pretty happy with this overall. We'll go ahead and get that code uploaded. Thanks again, everyone, for joining tonight. We thank you, Tansy, of course, there in the chat. Keeping it real. Tansy is my partner. She's over playing Minecraft, or as I like to say, doing vulnerability scans for Log4j.
For what?
Log4j. I'll tell you about it later. Yeah, Java folks, prayers up for the Java community right now. They're really going through it. But thank you all for joining the stream tonight. I really appreciate you watching. Once again, if you're watching the live stream on Twitch, check the channel description. You'll find links to my YouTube channel with all the stream replays there, plus the GitHub repo where I post all these solutions. If you're watching the YouTube replay later on, just check the video description right down there. You're going to find links to the Twitch channel with live streams, and once again to that GitHub repo with all of the code. Thanks for watching, and I hope to see you again tomorrow night. Bye-bye.